All right, everybody. Welcome to Class 2 of my Science and Religion class, or Quantum class, or whatever you want to call it. We're covering a lot of stuff. Obviously, quantum mechanics is one of the things we're really talking about, but in the quest to talk about that, we're going to talk about pretty much every area of science and be hitting on a lot of stuff. So, this class is called Detox. What are we detoxing you from? Well, you'll see. So, last class, if you remember, we went over the fun fact about the mass of the Earth being 5.97210 times 10 to the 24th kilograms, which is about 6 trillion kilograms, or 13.2 trillion pounds. And of course, I presented it to the class, and everybody voted, and pretty much we were 100% unanimous. Well, the choices were, if you remember, A, this is absolutely true, scientists know this. B, scientists can't possibly know this because there's no way you can weigh the Earth, so they're making it up. Or C, it's an educated guess. I mean, there's no way they can know for sure, but scientists are pretty smart, and they guesstimated. They guesstimated pretty close. So, how do scientists know this? Dang it, go back. Go back. Okay, the Earth's gonna come in. How do scientists know this? I mean, really? I mean, did they weigh it? Did they take the Earth and put it on a scale and somehow weigh it? I mean, how could they possibly have any notion of how much the Earth weighs? Now, obviously, we're not talking about, if we talk about the differences between weights, you can't really weigh the Earth in the sense you do we weigh ourselves on Earth because our weight is determined by, the force of gravity of us on the ground. So when I say weight, I'm talking about the mass. What is the mass of the Earth? So how do they know this? Well, let's find out. All right. So before we do that, before we try to tackle that, let's all get on one page here, and let's talk about some basic science. So when you drop a ball, it falls. Why? Anybody? Exactly, gravity. When you drop a ball, it falls due to the force of gravity. This thing here is interesting because, if you throw a ball and drop a ball, no matter if they start from the same height, they're going to fall at the same time. So if you shoot a bullet, and as soon as the bullet comes out of the barrel of the gun, you drop a bullet, those bullets are going to hit the ground at the same time. It doesn't matter how fast the bullet's moving, they're going to hit the ground at the same time. So Aristotle says that an object falls due to its desire to be at the cosmic center. Again, we can laugh, but we already discussed, what? It's pretty intuitive that the Earth is the center of everything, and that the Earth isn't moving, and that everything is going around the Earth. So to say that everything fell because it wanted to be towards the center of us, isn't too much of a leap of imagination. Really? Okay, so you have to admit it is sort of funny. Now, the ancients had no conception of the notion of gravity or anything like it. To even try to explain gravity, an invisible force to our eyes, would be ludicrous. Gravity is simply too complex of a concept to explain to a medieval thinker. Like it's too much for them. If you had to go back in medieval times and try to talk about gravity, they look at you crazy. So again, what is gravity? Yes, you. Gravity is caused by the centripetal motion of the Earth. Right. So the Earth is spinning. The Earth is spinning fast. Of course, we already discussed how, it doesn't really feel like the Earth is spinning. But the Earth is spinning fast, and that force is what causes us to be on the Earth. Okay. What about you? The weak force. Okay. The weak force is, we haven't even talked about that, but there's a force that is part of all the interactions between all the atoms inside of us, and that's what causes the gravity. All right. Well, let's get into it. What is gravity? Here's some popular notions when I talk to people. Objects fall due to the magnetic fields of the Earth, due to the centripetal motion of the Earth, due to the weak force, due to the downward pressure of Earth's movement around the sun. The Earth is moving really fast around the sun. And that pressure of going forward is what pushes things down towards you, kind of like a bug against a windshield. Here's the, here's the truth of the matter. A majority of people don't know. You have no idea what gravity is. And, there's nothing wrong with that, but, there's an important point to be made. Is that we want to claim scientists don't know what they're talking about, yet we can't even explain something as simple as gravity. Explain why, when we drop things, things fall. Now, of course, when I pose the question about the mass of the Earth, everyone's suddenly a scientist. Everyone's a genius. And everyone knows, okay, logically, no, they can't know that. There's no way you can know that. But yet, most people cannot even give you a satisfactory explanation of why, when you drop a ball, it falls to the ground. So look, I would never say this, but, yeah, most of you don't really know what you're talking about. I'm just being honest, me included, but, there's a point to this. So, ironically, the laughable statement that Aristotle made has more truth in it than anything most of us can come up with. How so? When we seek to describe gravity, we say things like, as many of you, if most of you, if you took any science classes towards the end of high school and you're really young, you'll still remember, the force of gravity is 9.8 meters per second. That's no matter what it is, that's the speed in which everything falls at because of gravity. It's due to the magnetic field produced by. Because the Earth is spinning, this creates a force. In essence, we're only able to describe gravity using other scientific terms that would then have to be proven. So we describe gravity as the centripetal force and all this. So, okay, so what is the centripetal force? Oh, that's the force of something spinning in a circle. Okay, so how do things spin in a circle? What forces are these? How do you prove these forces? Do you have equations? My point is that we use higher scientific concepts that really we still don't have a lot of knowledge about because we can't break them down scientifically or mathematically, and we use that to prove our point that we know something. Well, unless you can prove the foundation of what you know, you really don't know anything. More importantly, no one seems to know the fundamental truth that gravity represents. What does gravity represent? What is the truth behind what it really is? An object falls due to its desire to be at the cosmic center. Now notice how Aristotle's statement differs from what we put forward. Aristotle, I'm sure they could have measured speed and they could have said, oh, gravity is, whatever type of measurement they use, 8, pebbles per second it falls, whatever their measurement was. But he gave it's almost poetic, Here's an object that has a desire, okay? So objects have desires, and everything yearns just to be down, to be touching the earth, or to be at the very center of our earth is what it desires. Now, Aristotle made a statement revealing a truth. He wasn't giving principles. These were the ancient Greeks. They understood principles. They understood mathematics. They understood geometry. You have to read through geometry is birth, Euclidean geometry. Gravity, as we describe it, should be a function of a greater truth. So what is the truth that gravity points towards? What does gravity really tell us about our world? What truth does it reveal? All masses in the universe are attracted to each other. This is how Isaac Newton stated gravity. Or, to put another way, there is a universal force between all objects attracting them together. So if you happen to be listening to this and your mother-in-law is across the room and you can't stand your mother-in-law, I can tell you right now that you are attracted to your mother-in-law. Okay, that sounds really bad. But the point being is that there's a universal force. Okay, if you're watching this on your phone, there's a force between the phone and your face. The phone is pulling you towards its face, and your face is pulling the phone towards you. Every object you can imagine, there's a force between them. Here's the actual stated from Newton's universal law of gravitation. Newton's law of universal gravitation states that any two bodies in the universe attract each other with a force that is directly proportional to, and I left that out because in this, for this discussion right now, it's not really important. Because obviously, if you really talk about gravity and what you know about it, you get the idea pretty quickly that it is proportional. It's different. Obviously, most of you know on the moon, gravity is not as strong. That's why, the moon men, like you jump and you float down slowly. So gravity's weaker on the moon, Or if you're in space, everyone's just floating around like maybe there's no gravity. So maybe in space there's no gravity. Like, do you have to be on a planet? Do you have to be in space? You know, Gravity is obviously proportional to something. What that is doesn't really matter, but I put that in there for a couple reasons. So let's do an experiment, because this is a pretty bold claim. Because if I'm telling you that every object is attracted to every other object, that should not make sense to your mind at all. Because think about two delicate things. I mean, many of you as kids built a house of cards, and imagine the cards and their balance. And it has to be a perfectly flat table. There can't be any wind. Someone walks by too quickly. The breeze of the wind against their bodies could push down your house of cards. Now I'm telling you, well, every card is actually pulling towards each other. They're pulling towards each other. Everything's attracted to each other. You're attracted to the cards. So how come cards just don't fall down? How come if you balance a straw on a table, eventually the straw won't fall down because something pulled it towards it, not counting wind resistance or vibration? So here I'm going to show you an actual experiment. I just grabbed this from YouTube. You can watch these YouTube experiments all day. Okay, let's be honest. I just chose this video because that music was awesome. I have no idea what's up with people setting videos to random techno music or instrumental guitars, but it just cracks me up. But anyways, let's get an overview of this experiment, okay? Because it's kind of confusing. So you have a bar of styrofoam, something really light, okay? And on each end of the bar of styrofoam, you put a heavy ball of lead, all right? Too heavy, they're exactly the same weight. And directly in the center of the bar, you have placed a fishing line, very thin. Imagine a very thin but strong piece of fishing line balanced up towards the top of the ladder. Now, if you can imagine, that little thing underneath the styrofoam bar is it's like a Tupperware thing with water in it. It's not touching the styrofoam. The guy in the experiment, I don't know, he elaborated why he did that. It's whatever. Because he wanted to make sure the ground was perfectly level, or if there was any vibration or something, he would be able to see it in the water. But anyways, if you could imagine this, if this experiment was done, as soon as you let it go, it would what? It would spin around, spin back and forth around, and then eventually it would slowly spin. And if there was no wind, if there's no wind in this room, there's no AC, there's no current, there's no vibration. This room was in the middle of the flattest, salt bed desert in Utah. So no cars come by, no trucks. Nothing was disturbing this. Eventually it would sit exactly still. And you have to imagine this experiment is so sensitive that if you were just to blow on it very lightly, the thing would move. So we're setting up something that's very sensitive to force. All right, now watch this. Now you just saw the magic of gravity. And you could do this experiment at home. There's all different types of experiments where you can show, if you do something sensitive enough, that things are attracted to each other. So here's the point. What do we know? What do you know? What do scientists know? All right, we started talking about the Earth, and again, I just threw out, does anyone know what gravity is? Nobody really knew what gravity is, and I explained what gravity is. So, let's get back to topic. How do scientists know the mass of the Earth? Like, really, how can they possibly know this? Scientists know for certain the mass of the Earth by studying the motion of the planets. They had all this information by 1577. Like, this is medieval times here. Tycho Brahe, most of you never heard of him. He was the last of the great ancient astronomers. He produced a star chart in the late 1500s that was over 90% accurate compared to modern day measurements. He did this without a telescope, people. Most of us think astronomy, like, it's not even really astronomy unless you have a telescope. No, they had instruments, they had ways. He tracked the motion of the stars with immense precision. So here's a recap. 16th century scientists were able to observe the heavens without the use of a telescope, meaning Tycho Brahe's star charts, and attain accurate enough information to determine the mass of our entire planet. So I'm telling you, not only do scientists know the mass of the planet, they know for certain the mass of the planet. And not only do they know for certain the mass of the planet, they had this figured out 400 years ago. And people trip over the Aztec calendar. Really, I'm Hispanic. Trust me, it's my heritage. But look, we're going to go crazy over ancient stuff. Let's get crazy over the correct ancient stuff. So let me prove it. I'm going to walk you through step by step how watching the planets can give you the mass of the Earth, which shouldn't really make much sense, but let me break it down. So before we do that, we got to go through some basic astronomy, all right? Astronomy 101. Now, as many of you know, when the sun goes down, the stars in the heaven become visible. I'm not sure if many of you knew that. And the reason I say that is because in Phoenix, if you go outside at nighttime, there's a very high chance you won't see any stars. You may see one or two, like Venus, And most of the stars people think they see, if they stare at them long enough, they realize they're moving. And those aren't stars. Those are planes. Just throwing that out there. So the problem is us city folks don't get to see the stars because of smog and pollution and all that, Here's a picture I actually took outside. This is a typical view of the sky on a night in Phoenix. This is about as good as it gets. Not very exciting. After a rainstorm, a big haboob comes by, a good rain, and the next day, after the humidity, the clear, clean air, and you look up and, hey, now we got some stars. All right, so this is what we're working with. This is what the ancient people see. I can imagine why they looked up here and they were in awe, because these stars are so cool looking. No. This still doesn't do the heavens justice. If any of you gone camping, I mean camping, okay? I'm not talking about when you pull off on the side of the highway at one of those random campgrounds. I'm talking about you got to get away from the population. You got to do a lot of driving, a lot of dirt roads. This is what you can see. This is a view out backpacking in southern Utah. Now, you don't have to be in southern Utah. If you go to Mormon Lake, up on the Mogollon Rim in Arizona, for those of you that don't know, if you go up to Flagstaff and go east, about 15 miles, you can find a campground. And this is what you see. This is amazing. You can actually see the Milky Way. Like, this is not photoshopped. This is not made up. This is what you can see in the sky if you get away from all pollution. This is pretty remarkable. The North Star. How many of you heard of the North Star? Yes, okay. What is the North Star? All right, it points north. Okay, that's a start. In case you're lost, you don't actually need a compass. You just need to look for the star. And looking up into the sky at a star, you will then know what direction north is. No, but it's stars. And you watch Pinocchio, remember? Twinkle, twinkle, the North Star, make a wish upon a star. Oh, okay. The North Star, which is in the northern hemisphere, the entire sky pivots around this star. Now again, we don't really see stars, but if you were to stare up in the sky and stare at it long enough, you would see that all the stars move. And the only star that doesn't move relative to the other stars is the North Star. So quite literally, if you were to draw all the stars on a piece of paper, and you took the piece of paper and stuck it onto a bulletin board with the push pin in the middle, the push pin is the North Star. And as you rotated the paper around, those are the other stars. The other stars move, and they move around, but the North Star never moves. It is like a fixed point. Now, obviously, this whole sky moves across, just like the sun moves across the sky. It sets and it dawns. But you get the drift. This is the real significance of the North Star. Now, given that, so now we have all the stars that move around on a fixed circular coordinate system, and you have the North Star, which doesn't move. Well, what else is there in the sky? Some stars, however, don't follow this pattern. They move in their own unique way, independent of the fixed stars. So I just told you that all the stars can be put on a piece of paper, and a push pin can rotate them around. But on that piece of paper, there's 5 or 6 stars that would not work on that piece of paper because they do their own thing. They move and they do their own thing, and it always seems to look a little bit different. The ancient Greeks called these stars the wandering stars, or planetes in their language. So planets. So the planets are the moving stars. Remember, the ancients, when they were talking about the planets, they didn't know that they were round planets just like ours and that they were either made of gas or not made of gas, or, Mars to them was a moving star. Venus was the brightest, most beautiful star in the heavens. They didn't know it was a giant planet that was filled of sulfuric gas and toxic gas and uninhabitable. Didn't know that. So what does Mars do? All right. Now I'm going to show you the Mars's changing position relative to the fixed stars over a 2-year period. And Mars is sort of, and whoa. Okay, it just did a loop-de-loo. Mars did a circle. That is quite interesting. So that is quite strange. Here it is, taken with an actual telescope, time lapse, I think enhanced. Here's another view of Mars. Maybe the circle's not as pronounced. This is from April 2008 from 2007 to 2008, 1-year period. Here's the stars making a Z. So God is actually using Mars to spell out my last name, Zertucci. Very fascinating. Now, obviously, the perspective of the Earth has a lot to do with it and where you're looking at it. So, for example, here's the orbit of Venus, if you're looking at it over a time-lapse period from the African plains. That same view, seen from, Yosemite. It's just a different perspective. It's still the same loop, but depending on where you are in the Earth, northern hemisphere, southern hemisphere, it can be skewed and look different. This is an actual time-lapse video of, I believe, Venus and Saturn. I don't know. The bright one's Venus, but watch. And they're going, you know what? I'm going to go back the other way. And you know what? I'm going to turn around again. Let's take it with actual cameras. That's pretty cool. How many of you know what this is? Now, let me give you a clue. It's not an 8, and it's not an infinity. And if you saw this, most likely it'd be on a globe of the Earth. Anyone? This is what's called an analemma. So the position of the sun in the sky at noon changes from year to year. When the sun reaches its peak, noon, of the analemma, it is the summer solstice, and the bottom is the winter solstice. The vernal and autumnal equinox occur at the intersection point. So what do I mean? Let me show you. So if you were to look at the sun and mark its position in the sky every day at noon, and do this over and over throughout the entire year, this is the changing position of the sun. And when the sun completes this analemma, it's been approximately 365 days, 6 hours, and some odd minutes. This is how they knew the exact time of the year. The peak, when the sun's at its peak, that is the summer solstice. That is the longest day of the year. The very bottom of the analemma marks the winter solstice. That is the shortest day of the year. And the intersection point of the analemma is the vernal and autumn equinox. These is when the day and night are equal. This is the start of spring and autumn, I believe. I'm not sure. Not really into that. I don't. Right now, if you would have asked me what day Easter is on, I wouldn't be able to tell you. Most of you wouldn't, because the day of Easter changes based off of this. So if you actually follow this in the sky, you can realize the day of Easter. So ancient astronomers noticed that although the planets moved irregularly, they always appeared in the same narrow band of sky. Today we know that this narrow 9-degree wide section of the sky represents the plane of our solar system. All of the planetary orbits in our solar system lie in roughly the same plane. What does that mean? So if you were to take a sheet of paper and line up the orbit of a planet on that sheet of paper, every planet doesn't orbit on the exact same angle as our planet does. Otherwise, they actually be running into each other most likely, even though they're, they're different distances. Yeah. Now, if you took the orbit of every planet and you used a sheet of paper to mark it out, you would see that every orbit is not on the same plane. So this is exaggerated, but Mars rotates and obviously in a smaller orbit, but its plane, the way it orbits around the sun, is at a different angle than our planet does. But all the planets, all of them together, there's basically a 9-degree separation, so not very much. This picture is very exaggerated. It's probably more like 30 degrees. So, but it's exaggerated to give you the effect. Now, this isn't counting Pluto. Pluto's been demoted. It's not one of the planets. Pluto had a very, very high angle beyond 9 degrees. But the ancients didn't know about Pluto, so we're good there. So how did astronomers chart the movements of the stars without modern equipment? Well, the North Star acts as a reference point. Why? Because all the other stars pivot around it. So this is what they did. The observers imagined a celestial equator at the great circle of the celestial sphere 90 degrees from the pole star. The great circle represents the equator of Earth projected out into space. So if you take Earth and project it out into space, you have this imaginary sphere. And just like we have a North Pole, we have the North Star. That's like the equator. That's the fixed point which we can mark the movement of all the other ones, all the other stars. There's a close-up of that. You see our celestial equator. To measure longitude, observers made note of the constellations that straddled the zodiac, the 9-degree band of sky where the wandering stars appeared. The constellation or fixed stars are so far away that they do not appear to move with respect to each other. Ancient astronomers created a functional longitude coordinate system based on the 12 constellations that straddle the zodiac. Okay, so if you took this wheel, so to speak, and they split it all up to 33 increments, and in each increment, they noted that the main constellation in that increment, so Leo is the main constellation within that wedge. They use this, and since the North Star is fixed, and it's fixed on like the North Pole, an equator, they basically created in the stars a functional longitude and latitude. If any remember in school, you have the lines of longitude, latitude that scientists just came up with, and we draw them across, and that's how we get coordinates. Well, they were able to do this in the stars. Ancient astronomers divided up the 360-degree circle of the longitude on the zodiac into 12 sections of 30 degrees each, and named each 30-degree section for the most prominent constellation in it. So longitudinal stellar measurements were reckoned as follows. 22 degrees, 11 minutes, 6 seconds, Libra. So if any of you are familiar with longitude, latitude, and coordinates, it sounds familiar saying 22 degrees, 11 minutes, something, but they would add a constellation at the end because that would give them the position on the 360-degree wheel of their position of the sky about where something is fixed. So for every point on the Earth, we know like Columbus, right? He navigated using the stars. Okay, most of us don't even know what that means. This is what it means. His map, his whole function, his Google Maps, his GPS was in the stars. And now you know why he was able to do that, because of the fact that they were reliable, that they moved around the North Star. They moved in a fixed coordinate system. So given that, how did scientists explain the motion of the planets? Now you just saw Mars do a loop-de-loop. and it drew a Z in the sky. And we all know that they thought the Earth was the center and everything went around in perfect circles. Well, last time I checked, when things are going around in circles, they're not doing loop-de-loops like that, as far as in my view. Aristotle in physics represented the reigning church-endorsed scientific school during this era. According to Aristotle, action in the universe could only adhere to perfectly circular forms. Uniform, unchanging circles constituted the shape God found most perfect. So Aristotle, obviously the ancient Greeks were polytheistic, so Zeus and Athena and all the gods were so perfect that things had to operate on perfect circles, perfect spheres. Remember, this is the heyday of geometry, and the perfect circle and pi is a big deal. So they're like, look, they look up to heaven, they see this amazingness, and they're like, this is perfect, this is the realm of the gods, so things have to move in perfect circles. Obviously, the church later picked this up mostly due to the work of Thomas Aquinas, who said, like, on earth, in our earthly sphere, things fall. So that is the state of fallen man. And in the heavens, the outer celestial sphere, that is where the angels reign and where it's just perfect. And then you had hell and the 7 layers of hell, Dante's Inferno, and the lower layers. And so he worked it all out and tied the Bible into it and used church doctrine and philosophy to all make this make sense, so to speak. So that's when I say most of you like church endorsed, and you're saying Aristotle wasn't Christian, or or monotheistic, so to speak. But that's what I mean there. However, based on what we've already gone over, you can imagine that there may be problems with this model. We will soon see that scientists had to come up with all sorts of awkward constructions to model clearly non-uniform planetary motions, with mechanisms built out of circular orbs. So we'll start with Claudius Ptolemy. All right, he was in the ancient Earth-centered Greek model. He was in Egypt, but there was a Greek Egyptian. He basically, his formulation, his ideas in astronomy ruled Europe for the next 1,500 years. I mean, he was huge, and he was brilliant. Ptolemy believed the sun and the planets orbited the Earth, and he accounted for the irregular motion of the planets by spinning wheels that he called epicycles. So what's an epicycle? Here's Ptolemy's version of the solar system. So you have the Earth in the center, then there's the sun. Now here's Mars. Now Mars is actually not orbiting on the circle. Mars is orbiting around another circle. Mars is the red dot. So Mars is going around a perfect sphere, circle, and the center of that perfect circle is going around a perfect circle. This is what's called an epicycle. Now, what does that mean? Well, here, if you trace the motion, look at that. That's where you get the loop-de-loop. So he was able to account for the loop-de-loop and the motion of the planets based on using this type of system. But he had other issues. The next obstacle Ptolemy had to overcome was his geometrical explanation of the changing speed of the planets. He achieved this through the introduction of an equant. What do I mean? Well, when they analyzed the stars and they saw their movement, they could see that the planets change speed. In other words, when Mars does its loop-de-loop, it doesn't do the loop and move across at the constant speeds. There's times when it actually speeds up and it slows down. Now, this is an exaggeration, but basically they could see how when the planet gets closer to the sun, it moves faster. And when it's further away from the sun, it moves slower. So Ptolemy introduced what's called an equant. So here you have a point up in imaginary space. You have this line that goes across the circle called the line of epsides. The sun is offset, and there's this little magical point. Now if you look at the equant, or if you look at the planet, you see the planet still doing the same thing. The planet is slowing down, and when it gets closer to the sun, it's speeding up. But if you look at this little point here, you can see that it's going around the circle, a perfect circle around the equant, at a perfectly ordinary speed. So if you watch that, you'll see it's not speeding up at all. Now, obviously, this is all geometric. But using this device, he was able to geometrically explain the changing speeds of the planet. So here are the basic elements, right? The small dash circle that the planet is going around that imaginary point, is called the epicycle. All right. The deferent is the larger circle. That's what we originally thought the planet was just on its orbit. But since it's not really going around that circle, that larger dashed line is called the deferent. Now the eccentric is the x. So the Earth and the equant, which is that black dot, are offset by equal distance from the x in the middle, which is the eccentric. Now that's traditionally where you thought they believed the Earth was, but it's actually not. This is actually the geometrical representation of how Ptolemy worked it out. Now, of course, it's funny because we always see the medieval pictures of all the planets going around the Earth in perfect circles, and that is what they believed, but the learned people, the astronomers and whatnot, they understood that this is the only way it could actually work. Still perfect circles, they just didn't want to confuse, the lay people. So despite the fact that the system is considered to be geocentric, the planet's motion was not centered on the Earth, but is what's called the eccentric. Or the orbits of the planet in this system are epichroids. And here's a close-up. So the planets do not move in the traditional sense that you think they do. They're still using perfect circles. King Alfonso X, the Wise, King of Spain in 1252, after learning of Ptolemy's astronomical system, he remarked, "If the Lord God Almighty had consulted me before embarking on creation, I would have recommended something simpler." And I put this quote in here because it just kind of sums it up. I mean, you can imagine learning about this and learning how this is God, how God ordered the heavens, and you just can't help but think like, God, there's got to be a simpler explanation. Now here is an actual model worked out from the planetary systems. Now the reason why I put that in there is to make sure you understand how accurate this system works. So here all the planets are working on perfect circles. There is an epicycle. Everything is working according to the chart I just showed you. But you have to realize that this system, once you set it up, will accurately chart the planets for upwards of 2 years, where you can accurately chart the planets. So this is an extremely accurate system, despite how funny it may look. Now we get to Copernicus, which most of you have heard of him, 1473 to 1543. He was a doctor in canon law, along with being a physician, astronomer, translating, governor, diplomat, and economist. So he was a hardcore, devout Christian, knew the Bible in and out, but he was also an established scientist, economist. I mean, the guy was a Renaissance genius, so to speak. Now, he was smart. On his deathbed, he published his astronomical life's work, De Revolutionis Orbium Coelestium, basically the revolutions of the celestial orbits. The reason why he did it on his deathbed, obviously, is because, the Catholic Church, this is all during the Inquisition and whatnot, and he threatened excommunication, even death, for even talking about the Earth not being the center of everything. His groundbreaking work on a heliocentric model of the solar system would cause a firestorm. And here's the cover of his book, of course, all in Latin. But first, I would be remiss to mention the fact that, look, history is written by those who conquer, and in this case, and most of our history is an Anglo-type European slant. But when it comes to science, it very, very often gets overlooked that between the ancient Greeks and the revolution, the scientific revolution of the 1500s, it wasn't like nothing happened. There was huge breakthroughs in the Middle East and in India. Now, of course, you don't read about these in your history book. I would be remiss to fail to mention that history is often skewed by those who write it, and that Copernicus, while brilliant, certainly borrowed from other great astronomers whom European and American history selectively chose to ignore. The most famous is Aryabhata. He was the first in the line of great mathematician astronomers from the classical age of Indian mathematics and Indian astronomy. His works include the Aryabhatiya, and was 23 years old when he wrote this. I mean, this was during the Indian Renaissance, so to speak, in 500 AD, so roughly 1,000 years before the European Renaissance. And this guy, here's some of his works here. He broke down and could explain the lunar eclipse, solar eclipse, the rotation of Earth on its axis, the reflection of the light by the moon, the sinusoidal functions, the solution of single variable quadratic equations. He had the value of pi correct to 4 decimal places, and we all think the medieval people all thought the Earth was flat. Well, he not only thought it was round, but he calculated the circumference of the Earth to 99.8-degree accuracy, and the calculation of the length of the sidereal year, which we'll see its importance later. Now, of course, there were some ancient Greeks that also calculated the circumference of the Earth, but this was a major, major renaissance. And this is huge because this will feed into later the Persian Renaissance, who started roughly, it's in its height around 1200, 1000 to 1200, started around 880. Here's extremely favorite. Excuse me if I mispronounce this. Khajwa Muhammad, February 1201 in Khorasan, died on 25th of June 1274. He was a prolific writer, architect, astronomer, biologist, chemist, mathematician, philosopher, physician, physicist, scientist, and theologian. The Muslim scholar Ibn Khaldun considered Tusi to be the greatest of the later Persian scholars. He mathematically improved and perfected the heliocentric planetary model. Copernicus borrowed heavily, if not used identical methods, to his work in building his model. Now, this is being generous, but for the most part, if you look at the work, he stole a lot. He stole a lot because, hey, the Europeans thought they can get away with it and just steal from the Persians, And the Persians, of course, didn't steal, but they borrowed heavily and grew off of the Indian Renaissance by Aryabhatha. So my whole point is that, history is written by those who write it, and I think it's important if I'm going over history, to go over these guys. So moving forward, Nicholas Copernicus. Copernicus felt nature had to be simpler than Ptolemy's cosmology. He suggested that Earth and the 5 other planets orbited a central stationary sun. The back and forth wandering of the planets against the starry background was a result of our observation of them from an also orbiting Earth. All right, here it is. So here you can see Copernicus' explanation of retrograde motion. So the reason why we see Mars go in a circle is because Mars is an outer planet, and it is moving slower than us. We are an inner planet. Now it's easier to actually see in this next diagram. So here's Earth. You can see Earth as it moves around. It obviously moves much quicker than Mars. So in the time it takes Earth to almost go around the entire sun, Mars has only moved a little bit. Now this isn't exaggerated to kind of give you a clear example. But since Mars is orbiting more slowly than the Earth catches up with it and overtakes it. It is the overtaking that makes Mars seem to go backwards. So here you have the alignment. Then you see here as we're catching up, as we're getting closer. Now as we almost catch up, this is when Mars actually reverses direction, because now we are passing it. And then eventually as we go past it, so it's all just an alignment. This is why Copernicus thought that the sun was the center. It wasn't like he had some great epiphany, like, oh, why put the Earth in the center? That's so egocentric. No, this was an easier way to explain this retrograde motion, meaning the motions of the planets reversing direction, going in circles, making S's. Earth was simply the 3rd planet from the sun. Simplicity was hardly a compelling argument, since Earth obviously stood still. One felt no motion. You don't feel any motion on the Earth. A dropped ball would be left behind on a moving Earth. If the Earth was moving and you dropped a ball, it would blow away, kind of like when you drop a ball outside of a moving car. If Earth moved, a great wind would blow. I mean, that makes sense. I mean, like I said, we discussed earlier, the Earth is moving at 60,000 miles per hour around the sun. We don't feel a wind. I mean, you would think you feel somewhat of a breeze. I mean, that's very, very fast. 100 miles an hour is a lot of wind. Also, his system was seen to contradict the Bible, and doubting the Bible threatened salvation. Now, nowhere in the Bible does it say planets moved in perfect circles. This was all man-made, but the church adopted it, so it's more like contradicting the church. Church being the Catholic Church. So here's what Copernicus ended coming up with. So you have a circle on another circle, which is around another circle. So in the end, even though he got his idea by relating the fact that the Mars makes strange motions because we're moving faster, When he finally do all the math and geometry, he ended up having to come up with more epicycles, making a system more complex than than Ptolemy's. Because here you have Mars is rotating around a circle, which is fixed on another circle, which is fixed on another circle, which is going around the sun. So he really didn't realize his dream of making things simpler as far as motion. So the next thing is moving the sun to the center didn't prove as easy as he would have hoped. He hoped to get rid of all the epicycles altogether, but he ended up creating a more complex system of epicycles. So now we come to Tycho. This is when he comes in the story. Now he was on the fence as to which system to subscribe to. Due to his religious convictions, he disliked the sun being the center of our universe. However, he could not ignore the scientific facts. So he doesn't like the sun being in the center because that just doesn't feel right to him. You know, he grew up with Earth being the center. But then again, the data of the planets going around the sun makes more sense. So he says, look, the Earth is actually the center, just like, we've been taught. But the sun is going around the Earth, and all the planets are going around the sun. So he ended up coming up with a third system. It's quite funny if you look at it. So there's the middle Earth. That really fast spinning thing is the moon. You have the sun going around the Earth, and you have all the planets going around the sun. But if you look closely and fix your eyes on the sun, you'll see that the Earth is simply orbiting the sun along with all the other planets. So it's all just really a trick. It's easy to see when you animate it, of course. But it was just I just thought I threw it in there because I thought it was funny and sort of a middle ground. So the first question Copernicus thought after he had issues with the motion is, what are the periods of the planets? Meaning, how long does it take a planet to go around the sun? How long do they take to go around the sun? That's not an easy question since the Earth is a moving observatory. Remember, it's not like you can just say, oh, there's a planet there. Let me time how long it takes to go around. Because all the planets are moving, so is the Earth. Everything is moving in relation to each other. So to try to figure out how long it took another planet to go around the sun is not an easy question, and it did require some definite thinking outside the box. And to make matters more intense, not only are we going around, but we're rotating. So we're going around the sun, rotating in a circle, and we're trying to determine how long it takes other planets to go around the sun. So how did he do this? Before we can get into that, we need to go over some basic astronomical terms. First is an inferior planet. That is a planet inside the orbit of the Earth. So the two inferior planets would be Venus and Mercury. They're the two planets that are closer to the sun. A superior planet is a planet outside the orbit of the Earth. These would be all the other planets: Mars, Jupiter, Saturn, Uranus, Neptune, etc. Opposition. This is important. An opposition is an alignment of a planet, Earth, and the sun with the Earth between the planet and the sun. Now, obviously, only takes place for a superior planet that's further out. But this is when the planet and the Earth and the sun all line up in a line. It only occurs for a superior planet. It provides good viewing of a planet from Earth. Now, when I say it only appears for a superior planet, you may be thinking, why not for, Venus, if it lines up inside the orbit of the Earth and the sun, isn't it an opposition? But it has a different name. So if you're going to write anything down, write down this one first. Now, the opposite of opposition is called conjunction. This is when the Earth, sun, and planet are aligned with the sun in between. So this is the furthest distance the Earth is from a superior planet, is when they line up opposite of each other with the sun in the center. All right. For an inferior planet, when it's lined up, it's called an interior conjunction. This is when a planet is between the Earth and the sun, and they're all in alignment. So it's called an interior conjunction. That's an important term. The opposite, which isn't as important, is called a superior conjunction. This is when the sun is between the planet and the Earth, and they're all in alignment. Next is elongation. This is the angle between the sun and a planet, with the Earth as a reference point. So if you were to draw an imaginary line, just like this picture, from the Earth to the planet and the planet to the sun, the angle that you form with the sort of, right angle, triangle sort of shape, that is the angle of elongation. That's important, and we'll see why in a minute. For a superior planet, when the planet lines up to form a 90-degree angle, this only happens with superior planets, it's called the planet being at quadrature. So this is when an outer planet lines up with the Earth, just like you see here, and it forms a 90-degree angle. It's at quadrature. Next is the periods. And this is where it gets a little bit confusing, but hopefully I have a way to remember. A period is the time it takes a planet to go around the sun. But we had to break that down to two terms. One is called the sidereal period. This is the true orbital period, the time it takes a planet to complete a one full orbit around the sun. So the sidereal period is what you already thought a period would be, the time it takes to go around the sun. But just so we can be all on the same page with terminologies, it's called the sidereal period. And an easy way to remember that as being the one that is the real period is just remember real, sidereal period. This is the real time it takes for a planet to go around the sun. This is what Copernicus wanted to figure out. He wanted to figure out Earth takes 1 year to go around the sun. He wanted to know how long it takes Mars to go around the sun. So he wanted to know Mars's sidereal period. And it can't be measured from Earth because the Earth is moving. The next period is called the synodic period. This is the time that elapses between two oppositions or interior conjunctions. So basically when Earth and the planet line up, either with the Earth and the Sun sandwiched the planet in between, or with the planet and the Sun sandwiching the Earth in between. When they line up, you take a stopwatch and start it, all right? The next time those planets line up, you stop the stopwatch. That's the synodic period. It's the time that elapses between two of these either oppositions or interior conjunctions. And we already went over those terms, but those are when the planets align. Copernicus assumed all the planets moved at the same uniform speed. This was just, obviously this is how the heavens work, and this is how God ordered things, and planets all moved at the same speed. So given that, obviously if you have a smaller orbit and you're going at the same speed of a planet in its larger orbit, you're going to move faster in your orbit. You're going to go around quicker. Mercury's going to be going around a lot faster than Earth is. However, he noted that the inner planets move faster than the outer planets. That's what I just stated. Now these aren't to scale as far as how far away the planets are, but they are to scale as far as in the motion. So you see the inner planet is Mercury, really fast. Then the next planet is Venus, moving still pretty fast. Then there's Earth, a little bit slower. Then there's Mars. Okay, then you see Jupiter, Jupiter's a lot further out, but here it's a scale, they're all in there. It's moving slow. I think it takes 11 years to go around. Maybe that's Saturn, not sure. Then the next planet out is Saturn. And then, oh, did I lose my video? I'll play it again. And then you can see these two planets over here, Uranus and Neptune, they don't even look like they're moving. They take centuries to go around the sun. The synodic period is less than the sidereal period for a superior planet, and the synodic period is greater than the sidereal period for an inferior planet. Well, what does that mean? It means this. Obviously, the synodic period, so that's the line connecting Earth to Earth, that is obviously going to be less than the period that Venus takes when it lines up, because Venus is going much faster. So Earth goes ahead and makes it, 1/3 of the way around the circle. Venus went all the way around the sun and then went again. So it was moving much quicker, Obviously, the same is true for an outer planet. Earth is going to be moving faster than the outer planet. Now, Copernicus used these simple principles to calculate the sidereal periods of the planets from the synodic periods. So we're going to see very quickly, using some basic math, we can figure out how long it takes a planet to go around the sun just by knowing how long elapsed between us and the planet aligning in a straight line with the sun. So let's take P. P is going to represent the sidereal period of a planet. So for Earth, the sidereal period is 1 year. All right. Now, obviously, we're trying to find out the sidereal period for Venus, the little brown planet. E is the sidereal period of Earth. We're going to say that's 1 year. S is the synodic period of a planet from observation. So this is something we can measure. We know Earth's period, obviously, And we can figure out the synodic period, because as soon as we line up with Mars, we count down the days, and when we line up with Mars again, we have the synodic period. So if we assume the inner planet travels faster than the Earth, and that the Earth moves a fraction of an orbit, and the planet moves 1 plus that same fraction. Here in this picture, you can see that pretty clearly, that Venus went all the way around, so that's 1, plus that same fraction of an orbit that Earth moved. So 1 plus that same fraction. So you take the angular distance of a planet, so remember there's 360 degrees in a circle. So 360 degrees divided by p, the time it takes the planet to go around the sun, 360 degrees, and you multiply that by s, which is the synodic period. That's equal to the angular distance of Earth, which is just 360 degrees divided by e, our period, times s, plus 360. We add the one more circle. And you basically, the 360s cancel out and it breaks down into this. 1 over p equals 1 over e plus 1 over s. This simple equation basically will tell us what the orbital period is of any planet. So for Mercury, for example, when we line up with Mercury, we start our stopwatch, right? 116 days later, we line up again. Well, if we use this equation, 1 over p equals 1 over 365, that's our year, plus 1 over 116. If you solve that, you will get p, 88 days. It takes only 88 days for Mercury to go around the sun. So 1 year on the planet Mercury is 88 days. For the superior planets, it's a little bit different. It's 1 divided by p equals 1 over e minus 1 over s. So now let's take the equation and do Jupiter. So when we line up with Jupiter and start our stopwatch, it's 398 days before we line up with Jupiter again, as far as our synodic period. If you plug that in, you can see that the orbital period of Jupiter is 11.87 years. That's how long it takes Jupiter to go around the sun. So here we have it. Here are the planets, and here's their orbital period in years and their orbital period in days. Mercury takes 88 days to go around. Venus takes 224. Mars takes basically 1.8, almost double, 1 year, 321 days. Jupiter, 11.86 years, and Saturn, almost 30 years to go around the sun. Again, simple geometry, he was able to deduce these things. Next, what he really wanted to know was the distance of the planets from the sun. And again, he could do this using geometry. Copernicus was able to estimate the relative distance between the planets and the sun. He did this by knowing the periods of the planet. That's what we just showed. He knows how long, if you know how long the planets take to go around the sun, you can figure out how far away they are from the sun. Measuring the planetary positions in the sky and using some geometry and trigonometry. Since he wasn't able to determine the distance between the planets and the sun in miles, he formulated a common unit, a measure called the AU, or astronomical unit. Now you'll see this all the time. If you Google any planets or whatever, you'll see AUs. What AU represents is the distance between the Earth and the sun. Okay, so here we can see, here's D. This is 1 AU. So this is the distance between sun and the Earth. We're just going to call it 1 astronomical unit. So if Mars is 2 AUs away, we don't know exactly how far 2 AUs is, but we know it's twice the distance from the sun and the Earth. So at greatest elongation, so remember that angle, the term we went over. At greatest elongation, the view from the Earth is tangent to the plane's orbit, meaning if you draw out lines connecting everything, you actually form a right triangle. Well, now you should see we can actually get something from right triangles. If you remember from school, the good old SOHCAHTOA. So we know this angle, and we know this distance. We're just saying it's 1. So if we know the opposite, we want to know what the opposite is. And hypotenuse, we can use sine. So little d over big D equals sine theta. That's this angle here. And if you don't remember this from geometry, you may have to go over it and watch a quick YouTube video on that. So that simplifies equals D sine theta. D is just 1 AU, so D is equal to sine theta. So this angle is 18 degrees, D is equal to sine 18. Just plug it into a calculator. And that is it. And just using that simple math, he was able to determine now the distance between the inner planets, meaning this would work for Venus and Mercury. Now for the outer planets, he had to do a little bit more. Oh, hold on. I went back and now I have to pass these. Now for an outer planet, it gets a little bit more complex because we need to do a little bit extra math. So now we're going to do a planet from opposition to quadrature. Remember, quadrature is when the outer planet and the Earth, when you make a line, form a 90-degree angle. So first we need to find this angle here. And this angle is the angle from opposition to quadrature. So you have T. T is the time it takes for a superior planet to go from opposition to quadrature. And then you have E. E is the Earth's sidereal period. So that'd be 365 days. So if you plug that in, you'll get alpha. Now for beta, beta is going to be from here to here. Beta is, same thing, T, the time it takes for Earth to go around, 360 degrees divided by P. This is the orbital period of the outer planet. So if this was Mars, it'd be Mars's 1.8 years, however many days that is, to go around the sun. If you plug that in, that will give you beta. Now, of course, if you know alpha and you know beta, this angle right here is just alpha minus beta. And then we have the same situation we had with the smaller planets. And we can go ahead and solve for little d. And doing this, this is what he got. This are the distances of the planets from the sun. Earth is just 1, right? Venus is 0.72. So 0.7 of how far away Earth is from the sun. And Mercury is 1/3. So Earth is 2/3 out further than Mercury at 0.38, sort of ratio. Mars is 1.5 times further out. Jupiter is 5 times further out, and Saturn is 9.07 times further out. Now here's the crazy thing. These are his values he calculated 400 years ago. These are the modern values. You can see that he was pretty much dead on and most of his values. We do it with this Hubble Space Telescope and lasers and whatnot. This was all done using observation of the stars and geometry. Now comes Kepler. Kepler is the man. 1571 to 1630. He was a brilliant German mathematician, astronomer, and astrologer. It was in his day that he was burdened with grappling with 3 different planetary models to explain the motions of the wandering stars. Strangely enough, no clear criteria for physical truthfulness existed to discern which of these models corresponded to the actual physical universe. Each model could be used to predict the future longitude and latitude of the planets in the sky for a few years out. However, all of them became less and less accurate as time progressed. These 3 models, which seem radically different from a conceptual standpoint, all produce results which for all practical purposes are equivalent within a hair's breadth, as Kepler noted. So he had all these systems. He had the Earth in the middle, he had the Sun in the middle, he had the Earth in the middle with the Sun going around, the planets going around the Sun. And for all practical purposes, they had pros and cons, but they all worked very well for a period of time. And then slowly they went off, like a Rolex watch, just a minute per year. I mean, they would slowly fall out of alignment where they would no longer be useful. Because the whole point of a planetary model is you want to predict when star alignments, planet alignments will occur. So each model worked to work within a reasonable margin of error. But how then could he determine which model was true? Indeed, there was no way to determine the true organization and dynamics based on discrepancies between the models alone. So then Tycho comes, he's like, look, enough with enough. Let's stop arguing. What does the data say? Remember, Tycho did the star chart. He spent years, literally decades, over a decade, just charting precise data of the planets and their movements in the sky. Given that all 3 models produce absurdities of one like or another, Kepler would instead build his model on true data and observation, meaning Kepler's data. Sorry, meaning Tycho Brahe's data. The first thing he pointed out was the absurd conclusion that the Ptolemaic system gave for a given orbit. If you actually believe the Ptolemaic system with the orbitals and the eccentricity and all that, if you were to follow it through, this is the orbits of Mars, taken over, I think, a 15-year period. It's making pretzel. Now, how could you conceivably explain how this is just naturally how a planet moves? This is his data from 1580 to 1596. And here's his original drawing. Ptolemy's theory caused Mars to trace out a pretzel-shaped path. Scholars note that nothing like this had ever been published. It had apparently not occurred to anyone to consider the actual path traversed by a planet in the Ptolemaic theory. Now, Kepler's predecessors glossed over this. Even if they would have saw it, they're just like, you know what, don't worry about that. Because the state of scientific knowledge at the time was that humankind could not know how the heavens really worked. They declared that the heavens were made of an entirely different material called quinta essentia, or fifth essence, or fifth element. This enabled them to dispense with logical difficulties. The quinta essentia abided by different laws than the terrestrial sphere. Basically, you know what? Things work different in the heavens. That's why they're the heavens. So anytime they couldn't explain something in the heavens, instead of like pushing themselves harder, they're like, no, that's just the fifth essence. We just can't understand. That's how things move in the heavens, because that's where God is, and that's why things move differently. Kepler, he wasn't buying it. He thought God would not hide how the world worked from man, his creation. Men could know the mysteries of the world, including how the stars moved. He stated in his book, and I love this theater of this world is so ordered that there exist in it suitable signs by which human minds, likenesses of God, are not only invited to study divine works, from which they may evaluate the founder's goodness, but are assisted in acquiring more deeply. This to me sort of sums up the whole class, in that he was like, no, we can know. And not only can we know, is because God made us like him. We have minds like God. So we are not only invited to study, but we should, because we can learn more about his character and who he is just from learning about science. So Tycho and Kepler get together. As a student, he caught the eye of Tycho Brahe. His ingenious ideas were just what Tycho was looking for. Kepler saw this meeting with Tycho as an opportunity to work with him as an act of divine providence. Tycho was most interested in solving the puzzle of Mars's orbit, and hoped Kepler could help him unravel this mystery. Tycho was intent upon Mars, whose motivations provide the only possible access to the hidden secrets of astronomy, without which we would remain forever ignorant of those secrets. Analyzing data. It's important to know that Tycho's star chart was nothing more than a huge volume of raw data. Kepler, being a brilliant mathematician, along with an astronomer, was the perfect candidate to parse through the data and find meaning. So here's what it looks like. We all like to think Microsoft Excel is something 20th century, but it isn't. Imagine this, hundreds and hundreds of pages in these massive volumes, printed out. This is all painstaking data, and it's in a medieval Excel spreadsheet. Now, this would mean nothing to anyone. Now, Kepler, however, was a genius mathematician, so he was able to parse through that and make sense of it, and to use this data to help him prove what was really going on in our solar system. And here's a close-up. So how to figure it all out? The Earth, after all, is a moving observatory. The motion of our own planet skews our perceptions of the positions of the planets. So the first thing he needed to do was track the position of Mars. Astronomers realized they could combat the skew of the moving observatory through making measurements at opposition. Oppositions are moments when a planet and the Earth lie on the same plane in space with respect to the Sun. This enables an astronomer to chart the position of a planet with respect to a fixed reference point, which Kepler and Copernicus believed to be the Sun. So I told you what oppositions were, but if you remember, each orbit is on a different plane. So when the planets fall in opposition, so when Mars is in opposition with Earth, that's when the planes cross each other. So it's when they're on the same plane. When Mars is at opposition, it's on the same plane as us. That's why it's important, because we're going to need to track planets that aren't on our plane and move them to our plane. So oppositions are very important. The mean sun. Kepler realized that the process by which astronomers reckoned these critical measurements was flawed. Upon arriving in Prague, Kepler was surprised to learn that Tycho Brahe, like Ptolemy and Copernicus, he reckoned oppositions from the average or mean position of the sun, rather than the sun's actual position in the sky. When I found out during the first week that, like Ptolemy and Copernicus, he made use of the sun's mean motion, while the apparent motion would be more in accord with my own thinking, I begged the master to allow me to make use of the observations in my own manner. So what does that mean? The mean sun, Kepler explained how by Copernicus using Ptolemy's 15-year-old measurements to compute the sun's average motion, he inadvertently fixed the center of the line of sight for the measurement not at the sun, but at an empty point in the mathematical center of the orbit. Kepler sought observations from Brahe's tables where the sun set at the same moment Mars rose, or vice versa, indicating that the planets lay on the same line in space. So when the sun and Mars rise and set at the same time, that's when we're in opposition. So here's the thing. If you remember in the old school, the sun was offset, the eccentric was here, and the x was here. Well, they didn't really believe that the Earth was directly in the center, and the sun certainly wasn't in the center, it was offset. But when they did the calculations, they calculated the sun to be directly in the center, the mean sun. When that's not where the sun was, they believed it was a little bit offset. So if you look here, you'll see when they align, boom. Here you can see the orange line is what they calculated, when they should have calculated the white line, because that's actually the line of sight from the sun. And you can see how this angle represents the error against the zodiac introduced by the mean sun. And depending on how it is, the angle goes, it's way off over here. It gets a little bit less, then it crosses, then it'll get larger. Basically, their data was all off because they weren't realizing that they were calculating the sun in the wrong place. Now, referring positions to the ecliptic. In order to measure changes in the planet's longitude with respect to the fixed star, it was necessary to translate the planet's observed position onto the great circle on the celestial sphere that corresponds to the Earth's orbit, called the ecliptic, because it represents the plane where the ellipses occur. So in order to formulate things, we can't move stuff up here in three-dimensional space. We need to translate them and move them down here. To do this, astronomers would rotate the observed position down, right here, as if on the outside of a sphere on an arc originating at the node. So basically, if you take these two planes, right, this is a three-dimensional view, and if you were to look at them straight on, it would form two lines like this. So here's Mars at an orbit that's angled. We need to take Mars and rotate it down to our plane. And we're going to rotate it in an arc because this is all a celestial sphere. So we're going to not rotate it straight down, we're going to arc it down. That's what they call by measuring in the ecliptic. So Kepler realized again that the manner in which astronomers traditionally made this correction was flawed. The traditional method assumed that the line of sight to Mars and the observation originated from the Earth. Kepler noted that in measurements taken at opposition, the line of sight to Mars by definition originated from the sun. So remember, when the planets are aligned, right, Mars is outside the sun, lined up with us. So with that frame of view, with the sun directly behind us, you can sort of think of the light coming from Earth to the planet. However, when the Mars is not lined up with us, that's not the case. You can't think of the Earth light hitting Mars, because that's like imagining the sun in some imaginary point, which is what they were doing. They were failing to realize taking the actual line of sight from the sun. Again, you're getting a large offset. So here's a little diagram. You see Earth's orbit and Mars's orbit. They line it up, Mars as seen from the Earth. This is incorrect, and they rotate that down. they should be lining it up with the line of sight from the sun, which is there. When you rotate that down, it goes there. So again, Kepler found, and every time he found these, he went and just fixed all his data to get things precise. Next is he wanted to pinpoint the orbit of the Earth. Where exactly does our Earth orbit lie as far as in a circle? Kepler questioned how a planet could know how to move at a constant rate around an empty point. So great, this works fine, the planet going around an equate, but how does a planet know that? It doesn't make sense logically. However, computationally, Ptolemy's equate worked surprisingly well. So it works, but Kepler wanted to know, why does it work? Why? What physical cause did Ptolemy's equate device approximate? So what he did is this. He took two sets of angles. He basically experimentally tried to recreate Ptolemy's model. All right? So he took the sun and imagined that this is where the sun is and measured out all the sun's angles to Mars. Or by Ptolemy's definition, Mars moves at a uniform angular speed around the equate. So Kepler could match four hypothetical time angles that corresponded to a uniform speed for the planet, as seen from the equate, with four angles on the zodiac, seen from the sun, which corresponded to his actual observations. So these are the hypothetical angles, and these are the actual angles that he did, time angles from the sun to Mars. Oh, whoops. And this is the equate, that imaginary points, and this is its angles to Mars. And he worked them out, and after he worked them out, he could do this. Basically take them and then put them in a circle and then line them up where the points intersect. And he basically can recreate mathematically using the data, find the actual eccentricity between the sun and Mars. So he could basically map it out. Again, using oppositions. So Mars is in the same exact place every 687 days. So every 687 days, he marks Earth's position relative to Mars. And as he does that, once he gets enough points, he can determine exactly what circle the Earth is actually on. So the Earth lies on that bluish circle, not the dotted line circle. So again, if we assume the Earth moves uniformly, well, it moves at the same speed, all the angles around A should be equal, right? Because this Earth is where it's at every 687 days. So this angle, let's say it's 45 degrees, this angle should be 45 degrees, this angle should be 45 degrees. So since they're all moving, it's moving at a constant pace overall, these angles should be the same. Based on Tycho's data, Kepler's calculated angle AKE to be 42 degrees 21 minutes and AEK to be 96 minutes 22 seconds. I believe that's how you read it. I'm not sure. I'm not really good at the whole longitude latitude thing on maps in general. So setting AK equal to be 100,000 units. He just threw out a number because he needs a number, because what he's interested in is what they are relative to each other. He determined AD, the relative distance between Earth and the center of its orbit, to be right here, AD, or that actually should read AC. All right, well, let's say AC. AC, Earth in the center of its orbit, to be 67,794 units. He then computed the other distance ratio. So he computed AF, AH, AE. And you can see that these units were different. They should all be the same because this is a perfect circle. But they weren't. So this indicated that either A is not the center of Earth's orbit, or that the orbit is not a circle. And that leads us finally, based on this and a whole bunch of other stuff, he determined that the Earth does not go around the sun in a circle. That leads us to his famous 3 laws of planetary motions. The first one being, law number 1, that the orbit of a planet is an ellipse with the sun at one of the 2 foci. What does that mean? It's been a while since it's been in geometry. If you remember, a circle has a center. But mathematically, as you make an ellipse, those 2 points spread out, and those 2 points are called the foci. And you see the eccentricity, as they get closer and closer together to 0, it's a perfect circle. So 0 is a perfect circle, and as they move apart, the number gets higher. Eventually it'll hit 1, which is a flat line. So this is how we determine the eccentricity, is how much not a circle it is. So if you have an eccentricity of 0.1, you're not quite a circle, you're a little bit of an oval, The larger and larger number it is, like 0.8, that's not even close to being a circle. It's a major oval. Another property of the ellipse is if you were to take a bulletin board, and put a push pin in a string. The string is the same length no matter how you move it, and connect the 2 push pins, and you had a pencil here, and you were to move it around the 2 foci, you would be able to form that exact ellipse that corresponds to that foci. So basically, this is how it goes. Here's the planet. The sun is at one of the foci here. There's that other point here, it's just ignored. And this is how a planet goes around the sun. Now, obviously, this is majorly exaggerated, The reason being is, let's actually look at the actual eccentricities. Here we go. Earth's eccentricity is 0.01. Okay, so it's, for all intents and purposes, it's almost a perfect circle. But it's not quite. Obviously, Kepler was able to determine it's a little off. It's not a perfect circle. Mars, the reason why Mars did so much crazy stuff is it was a little bit more off. Now you can see here, this is a 0.2. So even though Mars is like, whoa, that's way off. I mean, if you look at that real quickly, you could probably say, oh, it's a circle. Now you look at it closely, you're like, it's not a perfect circle. But that's what you're looking at when you look at the orbit of Mars at 0.2. So you can imagine Earth, if we drew a circle with an eccentricity of 0.01, you probably wouldn't be able to tell, The moon is 0.05. I believe one of the moons of Saturn, I forgot which one, Titan or whatnot, has like an eccentricity of 0.000001. I mean, it's nearly a perfect circle. Halley's Comet, on the other hand, is 0.9. So that is a very, very, very obvious oval, or a very wide ellipse. So law number 2 is a line joining a planet and the sun sweeps out equal areas during equal intervals of time. What does that mean? Well, if you were to take, let's say every month, we're drawing a point and we're coloring it in. So each one of these colored wedges represents a month. All right, this is for Mars. What he said is, remember, he was trying to find harmony in the motion. Why does a planet move the way it does? And if it does speed up, like what order is that in that? What he found is, see this big long, imagine this is a big long piece of pizza, right? And this over here is a short and fat piece of pizza. These have exactly the same area. You were to take this, it takes no stretch of an imagination to imagine this triangle, and you stretch it out, and you can get this yellow triangle. In fact, every single one of these triangles has the same exact area. That's basically what he says, is that a planet moves in equal area times. Kepler discovered a planet sweeps out equal areas on the plane of an orbit in equal times. And his last law says the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. Really? What does that translate to? Now I'm using some geometrical terms, because a circle has a radius and a diameter, but an ellipse, they're different. You have the long radius, which is called the major axis, or the long diameter, which is the major axis, and the short diameter, which is the minor axis. If you do half of that, the very long, the longer radius is called the semi-major axis, and the short radius is called the semi-minor axis. So if we just translate in English, if you square the amount of time it takes for a planet to make one orbit around the sun, and you divide that by the distance between the planet and the sun, you get this. So here's all the data we found so far, right? Copernicus figured out the distances from the planet to the sun in AUs, relative distances, and he figured out the orbital periods of all the planets in years. Now when he looked at this data, this troubled him for the longest time because what's perfect? Like, it's not like these planets are perfectly spaced out, like perfect rings. Saturn's like a lot further out, and then there's Jupiter, and then all these planets are closer. Why? What was the reasoning for this? Well, if you take the orbital period squared and you divide that by the distance from the sun cubed, and you do that for all the planets, you see they all come out to 1 now, or nearly 1. But basically, there's some magical ratio he found. He called it the law of harmonies. He thought of it as chords or sounds that a singer makes, and he equated it to the heavens making noise like chords. And it got really complex, but basically, he didn't know why it happened. No one really knew why it was the way it was. But all of these were moving in accordance to some type of harmonious ratio, that being p squared, orbital period squared, divided by a squared. This was really his triumph of his planetary laws. And you'll see it comes into play later, and it's really important to figuring out the mass of the planet. So overall, these are the differences. The planetary orbit is a circle with the sun at the center. No, that's not true. The planetary orbit is not a circle, but it's an ellipse with the sun at the focal point. They always said the speed of the planet of the orbit is constant. It's always moving the same. No, neither the linear speed nor the angular speed of the planet in the orbit is constant. So our planet speed around the planet is never constant. It's always accelerating or decelerating, which is the same thing, but it's always accelerating. The one that is constant is the area speed. That's those triangle wedges, all have the same area. And then lastly, the square of the orbital period of the planet is directly proportional to the cube of the semi-major axis of its orbit. So if you square the time it takes for a planet to go around the sun, and you divide it by the distance between the planet and the sun cubed, they all come out to the same number. Aha, Newton. Newton's finally going to tie it all together. Born on December 25th, 1642, he's widely recognized as the greatest physicist of all time and the catalyst for the scientific revolution. In 1687, he published Mathematical Principles of Natural Philosophy, which is the greatest scientific work to ever be printed. It laid the foundation for all of physics. So what did Newton say? He revolutionized every part of science and mathematics. He formulated classical physics, created calculus, derived the universal law of gravitation, revolutionized the field of optics and telescope design, and finalized the formulation of the modern scientific method. Here's the cover of his book. Newton's 3 laws, the most famous laws that got it all started. Most of you should be familiar with these, but let's go over them anyways. Law number 1, objects in motion tend to stay in motion unless acted upon by an outside force. Now this is very counterintuitive if you think about it, because when you roll an object or send an object, roll it across the floor on the carpet, it, doesn't tend to stay in motion. Or maybe on a really smooth floor. But it stops because of opposing forces. The force of the carpet, friction, acting in the opposite direction will make that object stop. Law number 3, we'll skip over 2 for a second. For every action, there's an equal and opposite reaction. Meaning, obviously, if 2 people are pushing together like this, you have equal opposite reaction. But a better way to think of it is if you put yourself at an angle and put your arms against the wall, forming like a triangle, you're using all your weight and pushing up against the wall. But the wall is exerting an equal and opposite force and is pushing on you. Doesn't really seem like that. You're like, no, the wall is just the wall, like it supports itself. Or think about you standing on the ground. Your force is pushing down on the ground, but the ground, the earth, is pushing up just as hard on you. That's what keeps you in balance. That's what this law means. For every action, there's an equal and opposite reaction. And then there's the most famous. The force on an object is equal to the mass of the object times its acceleration. F equals ma. So it's probably the most famous of his equations. And it's the one you use the most, and it's the one that's going to tie everything together. But again, that doesn't seem very counterintuitive either, because if you're pushing something, right? Let's imagine you're pushing something across the carpet like a dresser. You're pushing it at 10 feet per second. And you cross a certain threshold, 10 feet per second, you cross a 10-foot distance. So in 1 second, you move across that. if you were to look at this equation, this is technically saying you have no force because you have no acceleration at this minute. You're moving at exactly 10 feet per second. You're not going from 9 to 10 to 11 feet per second. What we think more intuitively is about velocity. That's your change in distance over time. Your acceleration is your change in velocity over time. So F equals ma is not really as intuitive as we think. We think of it more of F equals mv. Velocity, it's 45 miles per hour, 45 miles per hour. Your acceleration is how fast you get to that, My car is a little putt-putt, and it can go 60 miles an hour. Who cares? But the question is how fast can it get to 60 miles per hour? The acceleration is really what matters. So Newton's biggest questions were, what force held the moons and the planets in orbit around the sun? We had the famous apple falling from a tree, and it always bothered me. I'm like, really? An apple? Like, it hit him in the head and suddenly he realized it was gravity? But that wasn't it at all. And there's a lot of conjecture around the story whether it's even true or not. But if there's anything true about this story, it's that when Newton saw the apple fall, at the time, what he was wondering about was how the planets orbit around the sun. Now, the planets their velocity is constantly changing. Their acceleration is constantly changing. And according to his formula, the planets have a mass, force equals ma, so there's a force constantly acting on them. The planets are either speeding up or slowing down. Their acceleration there's always a different acceleration, whether it's negative or positive. So he was wondering, what force is holding these up? Because if you think about it, if you have a circle, a ball, and you want to make it go in a circle, you have to push not only behind the circle, the ball, that will make it go forward, but you need to push also at an angle to make it go in a circle. He understood that if there was someone in the sun with a rope tied to the earth, he could make sense of circular motion quite easily, because the rope was that force. But there was nobody in the center of the sun, as far as he surmised, and there certainly wasn't a rope or tether connecting the earth with the sun. So what force held the planets in orbit around the sun? Or what force held the moon in orbit around the earth? When he saw the apple fell, what he realized was the same force that made the apple fall from the tree was the same force that kept the moon in orbit and the planets in orbit. Meaning, the moon is falling. Many of you don't realize that the moon is falling towards the earth, just like the apple. Here's what he gathered. It's called the famous Newton's cannon. So horizontal projectiles are in the air the same time it takes for something to just drop to the ground. Now this we know. So if you fire a bullet and you drop a bullet, they'll hit the ground at the same time. Now imagine if we fire it faster and faster. We get a more and more powerful cannon. So first we shoot it at 100 miles an hour, then 1,000 miles per hour. Now this is 10,000 miles per hour. Now we're going to shoot it at 20,000 miles per hour. And each time it goes further and further. But what do you notice? The earth is round. So since the earth is round, the cannonball will follow the curvature of the earth. So if you fire a cannon from a high enough mountain and it's fired with enough velocity, that cannonball will go in orbit around the earth, meaning the cannonball is falling. But the rate at which it's falling towards the earth is curving away from it. So it's never going to run into the earth. It's very intuitive. And here's his famous drawing from Principia. All right, so now let's break down how he used this idea and how we got to where we're at. So here you have the Earth, and the Earth is of a radius r. Now this is the one part where we're going to get involved with some math, all right? This is probably the only place in the course where we're actually going to get into some math. So I just ask you viewers to bear with me for the next 10 minutes, and because it'll be worth it in the end. And even if you get a little bit lost, it's okay, all right? So if this force were to disappear, or this tether, whatever's holding, or imagine this was, you're doing a slingshot, all right? David and Goliath. And David's swinging the rock around in a circle. So here's David, here's the rock. He wants to let the rock go at the instant where it lines up with Goliath, right? So as soon as you let something go in a circular orbit, it will continue on a straight path. So the whole point of a slingshot is to spin it around and let it go right when the angle of the circle lines up with your target, and that way it'll follow on with that trajectory. So the Earth at this moment, if you were to let it go, it would have a velocity go in this direction. At some time later, here, if we let the Earth go here, here's its velocity going this direction. So now if we take these two velocities, if we just move this velocity over, we have, this is the velocity that it would have been here, going this direction. Velocities are vectors, they have a direction. And if we let the Earth here, it'll have a velocity going this direction. Well, here we specify omega. Looks like a W, it's the Greek letter omega. This is the change in velocity. So between here and here, the change in velocity is represented by this W here. Then we write S. This is the change in distance. From here to here, we're going to call it S, the change in distance. So the change of your velocity is equal to your change in distance over your radius. We just make a simple ratio. Now we're going to go ahead and cross multiply. So omega is going to equal to SV over R. Now remember, what is our acceleration? Our acceleration is a change in velocity over time. So this omega is your change in velocity. So acceleration can be written as omega over t. Now if we go ahead and do plug and play, so we go ahead and plug in the SV over R in for omega, and we can solve simple algebra for, let me go back for a second, S over TV over R. Now S over T is what? Change in distance over time t. Change in distance over time is velocity. So you have velocity times velocity over R, which is basically velocity squared over R. So basically, we've solved the basic equation in physics you use all the time, and even your introductory physics course, is the centripetal acceleration. So the acceleration of an object in a circular orbit is velocity squared divided by the radius. Now, another way to write acceleration is in terms of distance. So velocity, remember, is your change in distance over time. So if any remember geometry, the distance of a circumference of a circle is 2 pi r. T, this t, the big T is the time it takes to go in one complete circle. So 2 pi r is the distance around the circle over t, change in distance over time. Again, if you go ahead and plug that into the v squared, you go ahead and plug this in and square it all, you get 4 pi squared r squared over rt squared. The r goes into the r up top, and you're left with 4 pi squared r over t squared. Now we've solved for the centripetal acceleration for a circular orbit. Again, basic physics equation, we're just breaking it down. Now let's go to Kepler's third law. Remember, Kepler found a unity, some harmonious way of getting all the planets involved. Newton saw this as a key to the force. Obviously, there's some constant. So the period, the time it takes for a planet to go around squared, divided by the distance from the planet to the sun, cubed, is equal to c. C is going to stand for a constant. We don't know what constant, we just know a constant. We need to start working these in. So if we go ahead and pull out the r and the t squared separately, we're just rewriting this. The reason why we're doing that is we want to work in our c. So if we go ahead and bring in c, you'll go ahead and see that the t's canceled. The r goes into the r, makes an r squared. And you can end up writing this as 4 pi squared c over r squared. So we brought the c in order of its terms. All right? So what we have here now is Newton solved for the centripetal acceleration for a circular planetary orbit. So this is the acceleration of the planets in an orbit. Now he had no idea what this constant was. He just knew that he could relate it somehow. So now let's go to his force equals mass times acceleration. Well, we have mass times, all this is our acceleration, 4 pi squared c over r squared. Now, what does Newton's third law say? For every action, there's an equal and opposite reaction, which is denoted by the F prime. So basically, if the sun is exerting a force on the planet to make it go around like a rope, then the Earth is also exerting an equal and opposite force on the sun. So if we write it this way, so m is going to stand for the mass of the planet. There's a force on our planet from this big C is some constant, but in this case, if it's being pulled by the sun, it's a constant that has to do with the sun. Some property of the sun we don't know about. But on the other hand, the Earth is pulling on the sun. So here, F prime, now we're going to use a big M for the mass of the sun. And instead of a big C, we're going to use a little c, because now the constant is an inherent property of P, being the planet. We're doing it on Earth, it's planet Earth. And obviously, equal and opposite reaction, we set them equal to each other. If we set them equal to each other, we can see that the 4 pi squared over r squared are common terms. We can cancel those out. And we get little m big C equals big M little c, which we also can write like this. If we do cross multiply, we'll get big C over big M equals little c over big M. So again, he's seen some type of ratio. Both these ratios, since they're in both terms, they are equivalent. So now he's going to rewrite them again. He's going to rewrite them as a K. All right? Again, for constant. We already used the C's. This constant is in relationship with the C and the M. Now, why do the 4 pi squared? Well, you can see the C and the M are here. And we have to, 4 pi squared is just a number. Remember, 3.14 squared, this is just a number. So we have to keep the number because the r squared is what this is all being divided by. So just trust me, it works out. So now we're going ahead and cross multiply. So 4 pi squared, we're going to multiply times c. So 4 pi squared c equals k times m. And then we're going to do the same thing with this little guy here. We'll do 4 pi squared little c, and then k times m. And we're left with these two equations. Now we have both the forces, and we need to do the sum of them. We need to multiply them. So we're going to do F squared. So F times F prime is we get m times 4 pi squared c over r squared times big M 4 pi squared little c over r squared. We're now going to multiply these. Now, since we solved, remember, we broke down the relationship further by using this new term k. So 4 pi squared c can be written as little k big M, and this 4 pi squared c can be written as big K little m. So we're trying to get rid of the numerical values and relate them all according to the constant. So if you do that, you get this. Km has been replaced by 4 pi squared c. This k little km is replacing the 4 pi squared c over in this term. And if you multiply those together, you get k squared, m squared, there's two m's, and then big M squared, and all over r to the fourth. And of course, as I'm sure you can tell, you can simplify that down to k m little m big M r squared. What we've just solved for, and this is for a perfectly circular orbit to make it easy. Obviously, we already discussed these aren't circular orbits, so in order to really do this in real life like Newton did, we have to use calculus, or he used actually a really complex form of geometry. But for our purposes, we're going to solve for a perfect circle. What we solved here is Newton's universal law of gravitation. That's what we discussed about before. Now we're going to rewrite it in terms of how it's commonly written. So instead of the K, we're going to change it to a big G. The big G, it doesn't stand for gravity, it stands for the gravitational constant, whatever that may be. It's the big G. Little g always stands for the force of gravity, usually on Earth. That's where we do most of our equations, and that's 9.8 meters per second. So here it is overall. Newton's law of universal gravitation states that any two bodies in the universe attract each other with a force that is directly proportional to the product of their masses, product is multiplication, and inversely proportional, which means divided by the square of the distance between them. So remember that force I said that it's between me and you and the person or any two objects? This is the equation that relates it. So your mass times the mass in question, if you multiply those together, multiply them times the gravitational constant, whatever that may be, and divided by the radius between both of you squared, that will give you the force of gravity between the two objects. So now you're probably wondering, like, wait a minute, I thought we were talking about the mass of the Earth. How do we get back to gravity? Well, if you're clever, you should see the answers right in front of you. See, big mass, little mass, forces between them. Force is equal to force, which is equal to G, m1, m2 over r squared. Well, what do we know? If we look at this right now, we know that the force of gravity on Earth is 9.8 meters per second, right? And we know our mass, or we know whatever we measure, whatever we can weigh on Earth, whatever's mass we know, we also know that it has the same force of gravity. 9.8 meters per second is everything on Earth. So this little m is, let's just say it's your weight, okay? And we know r. We know the radius of the Earth. Now you may be wondering about the radius of the Earth, but we know the circumference of the Earth. As you can imagine, it doesn't take, even a skeptic can believe that we do know how many miles it takes to go around the entire equator, okay? Of course, they figured this out in ancient Greeks, but if you only believe in satellites and lasers, we know exactly how many miles it takes to go around the Earth. And since we know that, remember, if we know the circumference of a circle, we know the radius of a circle. So we know the radius of the Earth, which turns out to be 6,378 kilometers. So the question is, what is G? What is that gravitational constant? And if we knew that gravitational constant, we can solve for what? The mass of the Earth. The force of gravity as we experience is the force that's between us and the planet. It's the attraction between us and our entire planet. That is the force of gravity. So if we only knew what G was, then we'd be able to solve exactly for the mass of the Earth. Now that actually isn't too crazy, because look at that experiment we did. Remember the experiment we went over? Again, what do we know? We know the mass of the big brick, right? We can weigh that. And we know the mass of the little ball. Okay, we can weigh that too. We certainly know the radius. We know the distance between it. We can measure that with a ruler. All we need to be able to do is measure the force. This thing is turning towards the brick. All we have to do is measure the force in which that thing is pushing towards that brick. And as you can imagine, we can do that easily in modern day experiments. And I'll show you how Henry Cavendish was able to do that 2 centuries ago. But as soon as he measured that force, he solved for the gravitational constant. Essentially, the experiment he did to solve this became known as the experiment that weighed the Earth. Because as soon as he had G, he can solve for the mass of the Earth. Because now we know G, we know how much you weigh, we know the radius of the Earth, and we know the force of gravity. Put all those together, and you solve for the mass of the Earth with exact precision. More importantly, once you know the mass of the Earth, you can use the same equation if you know the force of gravity on, let's say, Mars, or you know the force of gravity in relation to the Sun. You can then solve for the mass of the Sun. Once you solve for the mass of the Sun, then you can solve then for the mass of all the planets. You suddenly have, from Newton's universal law of gravitation, since everything seems to be related, everything's being pulled the same way from the Sun, you have a relationship to figure out what the mass is of all these massive bodies are. That is amazing. Here's Henry Cavendish. Henry Cavendish measured the density and mass of the Earth by calculating the value of G within 1% of the currently accepted value. His experiment became called the Cavendish experiment because there's no better way to do it. The way he constructed the experiment is the way to do it. And if you think about it, how did he do it? Now, obviously, here's another way of showing that experiment. You have a line, and the two balls attract to each other. And you can have a laser bouncing off a mirror to show how it moves. This is a more modern day interpretation of it. But the thing is, the way you measure the force is by measuring the twisting on the wire. So if you can imagine a rope, a thick rope, and you turn it with your hands, and eventually it stops. Because it only has so much of a it's what's called a torsional coefficient, and we'll talk about that in a second. But a force is an arrow. A force only goes directionally. A twisting force, a force that goes over a turn, is called torque. And we constantly hear about torque when you talk about cars and this and that, because obviously cars are turning motion, the wheels turning, the axles turning. It's all about torque. It's twisting. It's rotational forces. What he did is he devised a clever experiment to measure the torque. As this drifted towards this due to gravity, he was able to measure the force on this wire, and that's what allowed him to measure out the gravitational constant. So to go over it real quickly, we're going to go ahead and rewrite this equation in terms of g. So we're going to cross multiply. So g is equal to fr squared over mm. You write it for g. That's what we want to solve. And we know the radius, we know the mass, we know the little mass of all the balls, but we don't know we don't know g and we don't know the force, obviously. So we have one equation and two unknowns. Next is an equation for torque. Torque is equal to the force of that torque over L. L is the length of basically the distance between the two balls. So we're going to rewrite that in terms of F. F equals torque, which is the Greek letter tau, over L. But once again, we still don't know the force, and we certainly don't know the torque. So now we have two equations, three unknowns. Torque is equal to kappa times theta. Kappa, this K, is the torsional coefficient. Torsional coefficient. What the heck is that? That is the measure. As you can imagine, each type of rope that you can get has a different limit to how much you can twist it before it stops. That's the torsional coefficient. It's a measured number to say this is how much you can twist it. The angle is the turning angle of how much you can turn it through. So tau equals kappa times theta. But once again, we don't know t, we don't know the torque, and we don't know the torsional coefficient. So now we have three equations and five unknowns. Now we can write this, and this is again a whole different part of physics. I'm mostly putting this down for your notes, so you can sort of tune out if you want, just write this down. This is the t, the time it takes for you to twist a rope in this case to reach its limit is equal to 2 pi over I. This is what's called a moment of inertia over kappa, which is the torsional coefficient. And once again, we don't know the moment of inertia, we don't know kappa. So lastly, we can write the moment of inertia times the mass times L, the distance between the two balls, squared over 2. And again, you can put these in your notes and you can play with this later if you want. I'm just showing you how you solve it. So once we know I, we can solve for K. Once we know K, we can solve for T. And once he knew T, he could solve for F. And once he knows F, he can actually solve for G. And there you have it. Now I broke it down further just for you nerds if you really want to look. Obviously, if you really want to break it down further, you take this I and plug it in here. You get 2 pi, all this stuff squared over K, so ml squared over 2K. Then obviously we want to solve this to plug it in here. So we want to solve for K. So if you want to get rid of a square root, you remember in math class you got to square both sides. So t squared equals 4 pi squared. And then we square all this and we're left with just ml squared over 2K. We want to get the K over here. So we're going to cross multiply. And we're going to get 2K t squared equals 4 pi squared ml squared. And again, we want to solve for K. So we're going to divide this side by 2t squared. And obviously the 2 will go into the 4. So you're left with 2 pi squared ml squared over t. So we're going to go ahead, and this force is equal to torque equals k theta. So we're going to take the k theta and plug it into here. So the force is equal to k theta over L. K is equal to all this. So we're going to take all this times theta divided by L, or LT squared, and that gives us the force. And of course, the force is equal to this times r squared over m over m. And if you throw all that in there, so you add the r squared and add an mm, and then of course this m goes in here and cancels out, and this L goes in here and cancels out, you're left with this. Oh, sorry. Did it again. Dang it, slide. So, this is actually all you need to solve for the gravitational constant. Is 2 pi squared L theta r squared t squared over m. Again, you don't need to know that. I just thought I threw it in there. Probably unnecessary. The point is that you just need to solve for this gravitational constant, and then you could figure out the mass of the Earth. But here's the bigger question. What is the gravitational constant? This is the actual value of g. It's 6.67384 times 10 to the negative 11. Okay, that's 0.00000000667,384. That's length cubed divided by mass times squared. That's 6.67 100 billionths of a unit of 1. The question is, a unit of what? Now, we're going to have to go into that later. And remember, Newton had no idea what the gravitational constant was. It wasn't solved, obviously, for hundreds of years later. And even when he found the gravitational constant, we didn't really know how it would help them. But here's an idea. Fundamental forces. There are 3 fundamental forces in the universe. Oh, sorry, I got that wrong. There's 4 fundamental forces. I'm getting confused with 3 fundamental constants. The strong force. That is the strongest force that we know of, and that's the force that holds the protons and the neutrons together in the nucleus of the atom. All right. If we were to say that's equal to 1, so it's the strongest force. That's our standard. All right. The next strongest force would be the electromagnetic force. That's the force that holds all the atoms together. That's what holds us together. Gravity does not hold our organs together. Electromagnetic forces do, you know. That force is 0.0073. So that's 10,000,000. So the next strongest force is 7,000 times weaker than the strong force. It's 1/7,000th as strong. So you can get an idea of how powerful this strong force is that holds the nucleus of each atom together. The next one is the weak force. This force we'll talk about later, but it has to do with why atoms are radioactive and why radioactive isotopes decay and whatnot. If you look at here, it is much weaker. It's, oh Lord. It is much weaker. It's 0.000001. All right, that's 10 hundredths, thousandths, 10,000ths, 100,000ths, 1 millionth. This weak force, doesn't matter what it is, it's 1 millionth of what the strong force is. And then, of course, we come to the gravitational force. 6 times 10 to the negative 39. Like you said, it's a billionth of a billionth as strong as the strong force. So that's how you relate it. Gravity overall is the weakest of the forces. Now, obviously, it's stronger the bigger and bigger the masses are and over the distances, but you get an idea. That's 6 1 trillionth. Here are the fundamental constants. There are 3 fundamental constants in the universe. With these 3 constants, this is what everything else is formed off of. So kilograms, grams, pascals, Kelvin, Celsius, amps, volts, watts, pascals. Everything is made up of these 3 units. So there's only 3 units in the universe that will make up all other units. That's why they're called fundamental constants. The first one is the speed of light, which most of you knew. Didn't maybe realize, like everyone knows, nothing's faster than the speed of light. Now, whether you have any idea why you know that or if it makes any sense, we'll go into that later. But the speed of light is one of the fundamental constants. The second one you just learned is the gravitational constant. This constant is fundamental. No matter what you do, if you take the sun and the planets and you're doing it, this constant is equal throughout, no matter what the distances are. You'll see later that it could span the whole universe, and this constant is still the same. Planck's constant. This is what we'll go over next in next class, and this has to do with quantum mechanics. But these are the three fundamental concepts, just to put it all in perspective. So there you have it. We basically really solve for Newton's universal law of gravitation. But once you see Newton's law of gravitation, and we really took the time to break it down, you can see how once you know this number, finding the mass of the Earth is really simple. Because again, we know how much you weigh. We know the force of gravity on you is 9.8 meters per second downward. We know the radius, and we know g. There it is. A very simple fourth grade equation you can solve for the entire mass of the Earth. It's not impossible. Last thing, black holes. Now, we're not really going to talk a lot about black holes. I only mentioned it for this reason. Black holes, whether you know them or not, most of you know that they suck everything in. If anything gets close, it gets sucked in, and that they're so powerful, their suction, light can't even escape. And that's true. But here's the only thing I want to point out, all right? We're not going to go all in deep into black holes right now, is that they are extremely, extremely, extremely dense. Meaning, if the Earth got sucked into a black hole, the Earth would be compacted down to the size of about a marble. So I want you to imagine a marble that weighs for Americans, 13.6 trillion pounds. That's how much that marble weighs. Putting that in perspective, you can imagine how much these black holes weigh. If they're that dense, everything that gets sucked into them gets compressed to that tiny of a size, and these things are huge, hundreds of, we'll see they can vary in size, but they're massive. The one in the middle of our entire galaxy is relatively small, but it's still very big. It's about the size of all the way going out to the orbit of Mercury. So the sun would fit in there right about here. It's still very big. So if we were to look at our galaxy, you see here, there's a black hole in the middle. And that gravity is what makes the whole galaxy go around. That's how powerful that gravitational pull is. Our sun and our solar system is just a little tiny dot in the galaxy. And everything in the galaxy, all the solar systems, all the stars, and all the suns and all the planets, they're all moving around. Just like the planets move around the sun, they're moving around. And there's a black hole in the middle. So if we zoom in, well, here it is right here. So here's our solar system. This is about how big the black hole is in the middle of our solar system. It's tiny, but it's still huge. It's massive. But in our solar system, it's still, it's not that big. So if we zoom out, here's our entire solar system. You see the little tiny black hole. If we zoom out even more, this is our entire solar system seen as a star. And here are all the neighboring solar systems. So a couple hundred light years away, another solar system, more solar systems. If we zoom out, this is what's called our whole galactic neighborhood. Here are dozens of solar systems, all spaced out by thousands of light years. You can imagine how much of our whole entire solar system, which is billions and billions of miles wide, just this little dot, imagine how much space this is. This whole galactic grouping, this whole grouping of solar system is just a little tiny dot inside the galaxy. So you can see that black hole, how infinitesimally small it is, but how great its effect is. So things out here, which are literally hundreds of thousands of light years away, they're being pulled by the same thing. Their mass times the mass of the black hole, which is so massive you can't even imagine. But if you multiply those two together, multiply them by the gravitational constant, divided by the radius squared, and there you have it. They're all being pulled. Here are two twin galaxies. You can see one galaxy is being sucked into another one. Now these are millions of light years away. You see the gravitational effects not only in the galaxy, but they're affecting another galaxy. Here's a triple system. You see two big galaxies literally being sucked into each other, and you see a third little galaxy that's already in the pool of the other two galaxies. There's no limit in how far away the force of gravity acts in the universe. Now, with that being said, let's go ahead and watch a video. And there you have it. Our planets actually aren't even moving in circles. If you put it in proper perspective, they're actually moving in helix or vortexes because the sun isn't just sitting there. The sun is moving at 70,000 miles per hour around the entire, it's going to make a trip all the way around the galaxy due to that huge mass of the black hole, which gives it a very strong and very long gravitational pull, where it can reach things hundreds of thousands of light years away. It all just works together to that simple equation that we broke down. Now, of course, in perspective, the planets really do go in circles. It's all about perspective, okay? If you're bouncing a basketball up and down on a bullet train moving at 400 miles per hour, in reality, you're not really bouncing the basketball up and down because according to the ground and the speed you're moving, the basketball is really arcing back and forth in huge long arcs. But in the perspective of you, you're actually moving the basketball up and down. So from the frame of reference of our galaxy and looking at the sun, the planets, we're going in circles. But overall, since our entire system is moving, that's how it is. But of course, the whole galaxy is moving in the universe. And so you have that perspective as well. I just thought it's really cool to share that so you can get a breakdown of really what we did. So that's the conclusion to our class. We started with not even understanding how it could even be possible that scientists can know how much it weighs. And now you can understand that we not only know how much it weighs, but we understand so much more, all based off these basic principles that were built precept upon precept from the 1500s onward. And of course, we break things down even further. And those of you hardcore Einstein people in relativity, you know that this whole notion of the universal law of gravitation, the way Newton wrote it, is about to get rewritten again in a whole different light. But for all practical purpose, everything that I've described today still stands. But we're about to eventually, with Einstein, come up with a whole new crazy way of thinking about it. So that concludes this class. Next week, we will start going down the rabbit hole and break down atoms.